In a hypothetical meeting of two intellectual giants, 18th-century statistician, philosopher, and priest Thomas Bayes engages in a thought-provoking discussion with legendary game show host Monty Hall. Their focus? The perplexing Monty Hall Problem, a probability puzzle. In this imagined encounter, Bayes's pioneering work in probability theory and Monty Hall's real-world experience with game show dilemmas converge to shed new light on this enigmatic problem.
Good evening, Monty. I trust you're well.
Good evening, Thomas. I am, indeed. It's a pleasure to engage in a conversation with a brilliant mathematician such as yourself.
The pleasure is mine, Monty. I've heard you've been wrestling with a rather intriguing problem lately, the Monty Hall Problem. Would you care to share your thoughts on it?
Certainly, Thomas. The Monty Hall Problem is quite fascinating. You see, it's a probability puzzle based on a game show scenario. A contestant is presented with 3 doors, behind one of which is a valuable prize, while behind the other 2 are goats. The contestant makes an initial choice, and then the host, in this case, me, Monty Hall, who knows what's behind each door, opens one of the remaining 2 doors to reveal a goat. Now, the contestant is faced with a choice: stick with their initial choice or switch to the other unopened door. The question is, what should they do to maximize their chances of winning the prize?
Ah, I see. It's indeed an intriguing problem, and it has sparked quite a bit of debate. If I may, I'd like to offer a Bayesian interpretation of the Monty Hall problem. You see, Bayesian probability is all about updating beliefs based on evidence. In this case, we start with a prior belief about the likelihood of the prize being behind each door, which is 1/3 for each door initially.
That makes sense. So, after the host reveals a goat behind one of the doors, how does Bayesian probability come into play?
Precisely. Bayesian probability allows us to update our beliefs as new evidence is presented. After the host reveals a goat, our updated probability distribution should be focused on the remaining unopened door and the initial choice. The door the contestant initially chose still has a 1/3 chance of concealing the prize, but the other unopened door now has a 2/3 chance.
So, you're saying that the contestant should always switch, as there's a 2/3 chance that the prize is behind the other door?
Indeed, Monty. Bayesian probability suggests that switching is the optimal strategy because it maximizes the contestant's chances of winning the prize. It's a counterintuitive result for many, but the Bayesian interpretation helps clarify the reasoning behind it.
Let me interject for a moment to connect the brilliant mind of 18th-century philosopher and mathematician Thomas Bayes with the intricate web of knowledge we call Bayesian networks. Long before the era of modern computing, Bayes made his indelible mark on the realm of probability theory. His eponymous theorem, a testament to his pioneering work, laid the cornerstone for understanding how prior beliefs could be updated with new evidence to refine our understanding of the world. Now, fast forward to the digital age, where Bayesian networks have emerged as a powerful tool in our quest to model complex, uncertain systems. These networks, rooted in the principles of probability, intertwine variables through a graphical structure, reminiscent of Bayes's focus on conditional dependencies. Let me explain the key components and principles of Bayesian networks. Nodes. In a Bayesian network, nodes represent variables of interest. These variables can be discrete or continuous and are interconnected to form a network. Each node represents a probability distribution that quantifies the uncertainty associated with that variable. Arcs. The arcs in the network represent probabilistic dependencies between nodes. This graphical structure helps to visualize how variables interact with each other. Conditional probability tables, also known as CPTs, are used to specify the probabilistic relationships between parent and child nodes in the network. They detail how the probability of a child node depends on the states of its parent nodes. This is where Bayes' theorem comes into play to update probabilities based on new evidence. Inference. Bayesian networks enable inference, which means making probabilistic predictions or answering questions about the variables in the network. Given some evidence, we can use the network's structure and CPTs to compute probabilities for unobserved variables. When modeling the Monty Hall problem with a Bayesian network, you typically need 3 nodes to represent the key components of the problem. Contestant's choice. This node represents the initial choice made by the contestant. It can have 3 possible states: door 1, door 2, and door 3. This node is where the contestant's belief or probability distribution is initially represented. Car location. This node represents the actual location of the car, which is hidden behind one of the 3 doors. It can have 3 possible states: behind door 1, behind door 2, and behind door 3. The location of the car is unknown to the contestant. Host's action. This node represents the action taken by the host after the contestant makes their initial choice. The host's action is determined by the rules of the game and depends on both the contestant's choice and the actual location of the car. Note that the host knows which door the car is behind and will never open it. The conditional probability table of the host's action node shows that if the program contestant's first choice was wrong, for which there is a 2/3 chance, the host doesn't really have a choice of which door he opens. Only when the contestant's first choice was correct does the host randomly open one of the 2 doors. For example, if the car is behind the second door and the contestant initially chose the first door, the host will always open door number 3. If, on the other hand, the contestant selects door number 3, the host will open door number 1. Only if the contestant chooses door number 2, the host is equally likely to choose door number 1 or door number 3. We'll now explore how setting evidence in contestant's choice and host's action affects the posterior probabilities in car location. Let's start with our first scenario. The contestant selects door 2 and the host reveals a goat behind door 3. Watch closely as the Bayesian network recalculates the beliefs in real time, providing insight into the most probable location of the car. Now, in our second scenario, the contestant opts for door 1 and the host unveils a goat behind door 2. Notice once more how the Bayesian network dynamically updates its probabilities, offering fresh perspectives on the car's likely whereabouts. The network that is shown on the screen is available for testing in the BayesBox application. The link is in the description of the video. Now, back to the conversation between Bayes and Hall.
That's a remarkable perspective, Thomas. It goes to show how Bayesian probability can shed light on complex probability puzzles, like the Monty Hall problem. I appreciate your insights.
You're most welcome, Monty. Probability puzzles like this one are excellent examples of how Bayesian reasoning can be a powerful tool for decision-making in uncertain situations. It's been a pleasure discussing this with you.
Likewise, Thomas. I'll be sure to share this Bayesian perspective with future contestants on my show. It might just increase their chances of taking home the prize. Thank you for your time and wisdom.
As they bid farewell, each carrying the wisdom of their era, Bayes and Monty Hall left us with a deeper appreciation for the complexities of probability and a reminder that the pursuit of understanding, whether through philosophical musings or real-world dilemmas, is a timeless endeavor that continues to challenge and inspire generations to come. For more information about Bayesian networks, visit us at bayesfusion.com.